Hi everyone and welcome to PrepFusion. So today we'll be starting the lecture 2 of the state space. So in the previous lecture we learned what is basically state variables, what are state variables, what do we mean by state equations, and what is like the state diagram, right? So what is state variable? Basically the variables which are responsible for changing the state of the system are known as the state variables. What is state equation? The equation that we make from the state variable, that is the differentiation of the state variable on the left hand side with respect to time, and on the right hand side we have the state variables themselves and the input. The relation between those two are known as the state equation, and the pictorial representation of the state equation is known as the state diagram basically. Okay, so these things we learned. So now I stopped the video lecture basically because we didn't have enough time. I solved one question, we solved how to find the state equation and how to draw the state diagram from that equation. Now in this lecture we'll do more questions, basic questions, to understand the state variables and state diagram, all those things. So first question is this one. Basically we have to find the output uh, of this using state space, right? So what is the question asking us to find is find the natural response of the system where y of t is output and u of t is input. So we have to find the natural response. Now what do we mean by natural response? Natural response is the zero input response. When the input is zero, we have to find with respect to the initial conditions. So in like the basis of control system, in the last lecture there was a like question. If from there, if you have any confusion in this in the next few lectures also, that confusion will get clear. That is, what is zero state response? I hope you remember the name. Zero state response means the state, right? State values, the initial values of the state are zero. Okay, that is the basic normal that response that we get. That is also known as the force response, because we are forcing the input and we're getting some output, right? We're forcing the input to the system and we're getting some output. Now what is the natural response? So it is known as the, like, it is not the force response, right? It is the natural response. So we don't have an input, we don't force anything to the circuit. The circuit works as it is. So it has some initial state, and due to that initial state also we get some output. So that is the natural response. Okay, from there the natural name comes. I will also write this in one of the lectures. From there you will also understand. Okay, I will write all these things, don't worry. So we have been given the initial values of the state variables. So here it is like assuming the state variables this one, right? So what is this y of 0? Y of 0 equals to 1, and it is telling that y dash of 0, the differentiation of y at t equals to 0 is 0. So firstly, what is y of 0? So y equals to x1 only. So x1 is, here it is telling that x1 of 0 is 0, right? So sorry, is 1. So initial value of x1 is 1. So again, let me write one thing is, like, natural response means natural natural response means zero input response. That is, u of t is 0. That is source free response. Okay, that is source free response. So yeah, hence we will make our u of s as 0. So let me copy this sfg. This is basically the previous state diagram only that we drawn, right? That we solved. Okay, that is only that I am using to find the response this time, find the output using the state diagram basically. So we'll make our input 0. Okay, we'll make it 0. So we'll basically remove it. I will remove it in the next slide. Now what is this x1? This x1, right? This x1 equals to y only. So this value, right, is equals to y1 of 0 upon s. Okay, this value is y1 of 0 upon s. And what is this value equals to? This value equals to y2 of 0 upon s. Okay, y, so not y2 of 0, sorry, like this is the differentiation, right? This is the like x1t, x1t, right? And like what is x1t equals to sorry, x1 dash t, and what is x1 dash t? It is equals to y dash t only. So this will be y dash of 0. If you write the equations, you will understand by s. Okay, this is y dash of 0 by s. So this is x1 by s and this is x2 by s. Okay, now these are the values of the initial state equations. Now this y dash of 0 is 0, so this x2 of s, x2 of 0 is also 0. So this is equals to writing different color, 0 only. So this also gets cancelled, right? So we are only left with this. Now how we will solve? Okay, as I mentioned you earlier also, we can only solve using one input, right, in SFG. Okay, because it follows linearity, but we can solve for two inputs if I use the superposition. But here we have only one input. Why? Because this has become 0. Okay, this has also become 0. Only we have this input. Okay, so we will solve according to this. How? I will show it to you. From there you will understand. But first thing to understand is that even if this wasn't 0, what we have used, would have used that procedure, right? Use the procedure of superposition. First find the transformation for this, make this 0, then find the transformation of this, make this 0, then add those two, as I solved in the one of the lectures, right? So yeah, that's how we would have done if it wouldn't have been 0. So now what we'll do, we'll use Mason's formula. Okay, so what we'll do, we'll copy this. Okay, this is 0, right, and this is also 0, right? So okay, this whole thing goes off. This is also 0, right? So we are only left with this one, right? This one. Now this, I won't put the value of y1 of 0 right now. I won't put the value. I will put it at the end when I need to find the response. For now I need to find the transformation. SFG Mason's gain is used to find the transformation. Okay, so I won't put the value of y of 1 right now. I will just write y of 1 as it is. Okay, y of 1 by s as it is. So how we write the like the Mason's gain formula is output upon input. So what is my output? Output is y of s, and what is my input? Just remember, input is this one, right? y1 upon s. Input is y1 upon s. Okay, not just y1. Or you, what you could have done is put 1 over s here, but the general convention is we put y1 upon s like this, like the s term is with the initial value only. So the input is y1 upon s, not just y1. So it will be y1 of 0 by s. Okay, which is equals to, now what is the forward path gain? How many number of forward paths do we have? If I cross this path, right, now even if I go to this path, I will repeat this node again. So we have only one forward path, which is this one. Now how many loops do we have? So loops we have 2, simple SFG only. Do we have any isolated loops from this forward path? I think we have. This loop is isolated because no node is common for this forward path, right? So that was just a simple analysis. So I hope you are like super proficient in solving the SFGs, right? So you are very fast. So you have practiced enough questions. Okay, so this will be simply, what is the forward path? 1 times 1, 1 times 1, 1 minus, now what is the isolated loop gain? It is minus 2 by s, right? Minus 2 by s. So it is minus 2 by s divided by, what is the loop gains basically? So it is like 1 minus, we have two loops, right? 1 minus minus 2 by s is 1 and minus 1 by s square is another one. So I hope you can do it fast. I don't have to like explain it to you like all those things in detail, right? So minus 2 by s and minus 1 by s square. Do we have any non-touching loops? No, we have only two loops and they are touching here, right? So we don't have any two non-touching loops, right? So yeah, what will be the solution for this? If I multiply s square on both sides, I get s times s plus 2, and in bottom I get s square plus 2 2s plus 1, s square plus 2s plus 1. So like what is this s square plus 2s plus 1? It is simply s plus 1 whole square. So this y of s upon y1 of 0 of s equals to s into s plus 2 divided by s plus 1 whole square. Now I have to find the output response. Now what I will do is put the value of y1 of 0 right now. Okay, so what is y1 of 0? It is 1 only. It's to 1 only. So what is my y of s? It is equals to 1 over s times this one, right? S times s plus 2 divided by s plus 1 whole square. So what does my y of s become? It becomes s plus 2 by s plus 1 whole square. I can also write this as 1 by s plus 1 whole square plus 1 by only 1 by s plus 1 or and 1 by s plus 1 whole square. Okay, so this is basically the y of s in Laplace form. Now I have to find the time response, so we take the inverse Laplace, right? So if I take the inverse Laplace, what do I get? Y of t is simply equals to, if I take the inverse Laplace, this is exponential only, e raised to power minus t, but this is ramp only, right? This is ramp only. So what do we get? We get e raised to power minus t into t. I hope you are like totally fast with this. Like you don't have any issue with understanding this, right? This should be tip of your mind, right? All these things, tip of your tongue, whatever they say that term. So this is u of t. Okay. So yeah, this is our output response. I can write this in a better manner, like 1 plus t. Now this u of t, right? This is not the input this time. This is the unit step. So there may be a bit of confusion with u of t. All these things. You can write the input as c of t also for your so that you don't get confused. Okay. So this is u of t only, and this is the output. So basically, this is the, what is this? This is the natural response, right? This is the natural response. Okay, this is the natural response. So yeah, now let's solve another question here. This is the more simpler question. What is the question asking us is, find the transfer function of the system where y of t is the output and u of t is the input. Okay, we have to find the transfer function, right? For transfer function, what do? We make the initial conditions as 0. So we have only one input and one output. So very simple, just use the Mason's formula. Okay. So we have to find the forced response. Transfer function is the forced response, which is basically y of s upon u of s when the initial values are equals to 0 basically. Okay, initial values are 0. Okay, so simple SFG only, so you are expert at this, so I don't need to solve this, but still you will solve. Okay, so I think you have solved like this SFG multiple times. Right now you have practiced it many times. So using the Mason's gain formula again, let me take it to the next page. So y of s upon u of s, what will be, like how many number of forward paths we have? We have only one forward path, right? We don't have any other, because this is coming back instead of going away. So we have only one forward path. What is the gain of that forward path? It is 1 by s times 1 by s, so it is 1 by s square. So simply 1 by s square. Now do we have any isolated loops? No, because we have only these two loops, and these two are like with the forward path itself. So our associated loop gain will be 1 only, so it is 1 minus 0. Okay, now let's find the determinant, right? So we have two loops, one loop gain same, the determinant will be same for the previous case also and this case. Like for SFG, you know, right, the determinant remains same irrespective of the input and output, because it's the same SFG. So loops will remain same, right? So it is minus 2 by s and minus 1 by s square. So 1 minus 2 by s minus 1 by s square. Okay, so again multiplying denominator and numerator with s square, what do I get? We get 1 divided by s square plus 2s plus 1, right? 1 plus s square plus 2s plus 1. This is basically my transfer function, which is equals to so what will be, well, like this is basically my transfer function. This is the calculation. Impulse response, what will it be? It will be t e raised to power minus t u2, but that is not that, like the question has not asked that. The question has asked only the transfer function. So this was like it for this question. Now what we will do is we will write the state equation using the state diagram. We will go backwards now. Okay, we'll go backwards now. The same question only. So we'll write the state equation using the state diagram. Now this is very important. Okay, you have to understand like how we write this, right? So it's just not like simply here I have sx2 and I will add minus 2 here and minus 2 sx1 here and minus 1 x1 here. No, we can't do that. Okay, we can't do that simply. Okay, because there are nodes outgoing here and multiple nodes incoming, and those nodes are related with some other nodes. Okay, so we can't do that. So there are particular steps that we need to follow, that we'll do. Okay, what we'll do? Step 1. What will be step 1? So step 1 basically will be to remove the initial conditions. Okay, because that step came only into Laplace domain, right? In state equation we didn't have any initial condition, right? But in Laplace domain we had the initial values, so we have to remove the initial condition. Okay, so I will copy this. Now what I will do is remove this initial conditions, right? Okay, this is not the state diagram. What we are trying to do is find the state equation from the state diagram. So this one was the first step. We have to remove the initial conditions. Now what will be our next step is basically convert this state diagram into from S domain to time domain. Okay, so what we will do, we will convert this state diagram into time domain instead of Laplace domain. into uh, into time domain basically. Convert the state diagram into time domain. Okay, so now I will copy this again. I'll copy this again. Okay, and what I will do is write the time domain expressions. So this u of s, what will it become? It will become u of t. And this sx2, what will it become? It will become x2 dot, right? X2 dot. This sx1, what it will become? It will become x1 dot, which is equals to x2 itself, right? X2 itself. Why? Because we're integrating it. We're integrating it. And okay, sorry, this x1 of s will become x1 of t. Let me write all this in different colors actually. Okay, so we have converted, and this y of s will become y of t. So I have written the time domain expression. Now what will be my step 3? As I have already taken the effects of this 1 by s, right? All these things I have taken consider in the time domain expression. I will remove this. Okay. This will be my step 2, 3. Step 3 basically. Remove the 1 by s terms as effect has already been taken. Okay, as effect has already been considered or taken. So what I will do, simply remove, like, this Laplace terms also I will remove. Okay, this 1 by s terms also I will remove. Okay, so what is this? This one is x1 dot. Okay, and this one is x2 dot. Okay, this one is x1 of t. This one is y of t. So this one is basically u of t, y of t, x1 dot, x2 dot. Okay, so all these things we get. So now we can write the relations, but still we will use the Mason's gain formula only. What we will do is, what is the step 4? Let me copy this again. Step 4, right? What we will do is write the cause effect. Let me write this better. Cause effect relation using the SFG, right? Using the simple SFG. Okay, so what I will do is write the cause effect relation, but one thing to note is that this will work here, but if there are multiple nodes coming in, right, going out from this x2 dot also, like some node is coming connected with this node also, then I won't be able to directly write here. I will write this directly, but sometimes what happens is we won't be able to directly write all when we will not be able to directly write, I will solve a question from there, you will understand. Okay, but as you can see, what is like this equation is already known to us, right? This is one state equation. So like the first equation is this output equation, right? So this is the output equation where y of t equals to x1 of t. Okay, now this is the second equation where I can see x2 dot of t, x2 of t equals to x1 dot of t. Okay, and this is my third equation. Basically we see two nodes incoming, right? And this is only x1 of like this is only x2 of t and this is only x1 of t. If this has also something incoming, right, then I wouldn't have able to write this. Then what I would have like I had to do is was like find the transformation for each of the case. I will solve one question from there, you will understand. Okay, just as we have only this is only x2, this node is only x2 and this node is only x1, so I can simply write the cause effect relation here. How will I write? So basically this is x2 dot of t equals to what is incoming here, minus 2 times x2t, right? But first I will write x1t. So x1 of t times minus 1, so minus of x1 of t, and what is incoming here, it is minus 2 times x2 of t, so minus 2 times x2 of t, x2 of t. Okay, so this is x2 dot of t. Also another thing is incoming, right? This one, right? The input is also incoming, so it is 1 times u of t, 1 times u of t. So I got the three equations, right? These are the state equations and this is the output equation. So output equation, this is a state equation, this is also the state equation. Okay, so these are my three state equations. So let me like write the matrix format. So what will be the matrix format? Simply like as we started, right? Just like we started. So from the differential equation, so x1 dot of t, even if I don't write t, right, in bracket, you have to understand that this is a function of time. Okay, that thing you have to understand. So what is x1 dot of t? It is simply 0, like 0 times x1 plus x2, right? So 0 1, and this is minus 1 times x1 minus 2 times x2, so minus 1 minus 2, x1 of t, x2 of t, plus what is the input, right? What is the input? Basically what is this input? So this input, right, it is simply equals to 1, like x2 dot is related with 1, but here x1 dot is not related with the input, so this will be 0 and this will be 1. How am I writing the orders? All those things we'll understand in state space representation in the, I think, in the next lecture itself. So this is the state equation, state equation. Okay, and what is our output equation? So my output equation, right, y of t is simply equals to, how is it related with the state variables? It is not related with the x2, it is only related with the x1. So 1 0 times x1 of t, x2 of t. Let me write this properly actually. And is it related with the input? No. 0 times u of t. Now you may ask why I wrote it like this. All this I will explain it to you in the next lecture, okay, in the state space representation. So basically this how is this row vector, why is this column vector, and why is this vector square matrix, basically we'll understand it. We'll all understand in the next lecture. So this is the output equation. This is the output equation basically. So this is like it for this lecture. Okay, I'll just quickly revise you what we did in this lecture and in the previous lecture. So in the previous lecture we had a differential equation, we converted it into state equation. From there we go into state diagram, then we got the state diagram. From there we have to find the natural response of the system. What do you mean by natural response? Is that the response of the output, the response of the system due to the initial values of the state variables, right? State variables that we found out. Okay, we made input 0 and other initial value was also 0. If it wasn't 0, what we would have done is find the response due to the first initial state variable, initial value of the state variable. Then we would have found the response due to the second initial value of the state variable and added those two up, right, using superposition. Okay, that we would have done in this system. So yeah, this was the natural response. Then what we did is find the transformation. In transformation, what do you do? We make the initial values 0. So initial values of the state become 0. We have only one input and output. Simple only, right? We have solved this many times. So we use assumption and solve this. In the next, what do you do? We go in the reverse direction. From state diagram, we have to write the state equation. So there are 4-5 steps. So first is to remove the initial conditions. The initial conditions came due to Laplace domain, transformation of the Laplace domain. So we remove the initial conditions. Then what do you do? We convert the state diagram into time domain, because at the end we have to write equations, state equation in time domain only. So we convert this into time domain. How I did that, I explained it to you, right? Then I remove the 1 by s terms. Okay, this is not 1 by s actually. I remove the 1 by s terms. Why? Because we have already considered the effect in time domain, the differentiations, right? So I don't need the 1 by s terms only. I don't need the 1 by s terms anymore. Then what I do is write the cause effect relations. Now here, as this x1, right, x1 dot doesn't have any other incoming nodes, I can simply write this equation here, this node, right? But in the next few examples I will explain it to you. We won't be able to simply write these equations just in one line, right? We have to use the Mason's gain formula. How and why, I will explain it to you in next few lectures, right? But here I will simply write it in one line because this node doesn't have any incoming values, right? This is also x1 and this is x1 dot. Okay, so yeah, we can simply solve it like this. And this is the output equation. Like this is known as the output equation, and these are known as the state equation. The state variable equations are known as the state equation, and the relation with respect to output is known as the output equation. And we wrote it in matrix format, and yeah, that's it. Like that's the solution of this question. So that's it for the lecture, because like in the previous lecture I couldn't complete the questions, that's why I had to take an extra lecture. So the next lecture we will study about the state space representation.